एनी व्यूअर करके ऐप है, वो दोनों में डालनी पड़ेगी।
हैंग हो गया लैपटॉप। लैपटॉप हैंग हो गया, क्या करूं?
अभी नहीं हुआ वो
हो गया लैपटॉप हैंग हो गया, उसका क्या करूं?
अलाउ।
वो अलाउ करने पे यहाँ पे कुछ नहीं आ रहा है, यहाँ पे कुछ नहीं आ रहा
रुको रुको। एनी व्यूअर करके एक application है।
So good afternoon everyone. So this is week 4 of the course Fundamentals of Nano and Quantum Photonics. So today we will study about scattering of electromagnetic radiation. So in the previous week we learned how optical properties of materials can be modeled, and we saw Lorentz model, Drude model, and so on. So this will we will completely talk about plasmonics, like uh, like how the surface plasmons propagate, what are LSPR, SPPs, bulk plasmon. So in this lecture we will talk about these things. So this week we will talk about plasmonics. So what is the historical motivation? So when we started about this course, then in the very first week we showed that this Lycurgus cup, so which exhibits different colors depending on where the optical illumination is. So this is a 4th century Roman artifact. So you will see that in the reflection mode the color is green, whereas in transmission mode it is reddish. So depending upon the where the optical, so since the red color is shown in the transmission mode, suppose if you have some light source inside the cup and then you are passing the light through the cup and you are observing outside the glass, so then it will appear reddish in color. The second example is the stained glass windows in Europe. So you saw that this is these, whenever you go to church there are different colors. So these colors are due to gold or silver nanoparticles. कोई है आज तो कोई वो भी कर रहा है. So these colors are because of the metal nanoparticles. Some gold and silver nanoparticles are mixed with the glass. So that's why we are able to see different colors. In reflection mode and the transmission mode, we see the different colors. So now next we will talk about the plasmon. So what is plasmon? So plasmon is a quasi particle, or we can say that a collective excitation that occurs when a photon will interact with the electron in a matter. So plasmon, we can think of the plasmon as a photon coupled to an electron. So whenever the photon will interact with our electron, we refer to as plasma. So plasmon is a quasi particle that represents the light matter interaction. So this interaction occurs in metals as well as nanostructures. So what is the scattering? So we saw that in the previous lectures, if light interacts with the material, there are five main phenomena that could occur. That is reflection, refraction, scattering, photoluminescence. So these are the main phenomena, and here we were talking about scattering due to the nanoparticles. So when the light will interact with a smaller object, it will induce the polarization, and in the dielectrics, bound electrons oscillate, and in metals, free electrons oscillate. So you know that in dielectrics we need higher energy to move from the valence band to conduction band, and in the metals there is no band gap, so electrons can oscillate freely. So if we consider a spring mass system wherein we can think of an electron bound to a nucleus through a spring constant, so there is a characteristic resonant frequency, and then we can describe the response of an electron. So the same phenomena we can apply on the nanoparticle. So suppose if we have a nanoparticle or a micron size particle, so when light will incident on that particle, it will cause some polarization. Because of that polarization, so what is mean by polarization? That there is a charge separation in the presence of electric field, and it will create a dipole, and because of dipole there will be induced polarization. Because of that, this oscillating dipole will radiate, and that we call scattering and or secondary radiation. So we define the, so we can capture that polarization in terms of Lorentz model. So capital P. Okay, so just a minute. I think there's some problem. There is some technical glitch. So
Anywhere, anywhere.
there is some technical glitch. I'm unable to cast.
Gmail. So Gmail को
Just give me 5 minutes. I will continue. 573 588 275. Parallel at the rate 123. FGU ZY 131. Hmm?
तो हम लोग इसमें कनेक्ट करना चाहते हैं।
Session 2.
हाँ,
है ना?
ये पुराना वाला ये तुम्हारा है। ये है
Okay, since I'm unable to.
ये 568 599 015 5685 current is 0.
Okay, so what was our conclusion that from the formula? So I am unable to cast my screen on this laptop. So you just I just want to show you the formulas from the lectures. This was the formula that I was talking about, that intense scattered intensity by a dipole. This is represented by this. and then Lorentz model, and using Lorentz model, what will be the scattered intensity by the dipole. So this part, 1 upon omega naught square minus omega square minus iota gamma omega, it represents the resonant response of the particle, and EL square is the incoming intensity of the light. So the what are the conclusions from here? That strongest scattering near a resonance, that is near resonance, it means omega will be equivalent to omega naught, and stronger scattering for higher omega, or we can say the shorter lambda. So because it is we can see that it has a dependency of omega ka power omega raised to power 4. So it means for the higher frequency there will be more scattering. For it means for the larger wavelength the scattering will be lesser, and the scattering can occur both in the forward and backward direction. So next, this question arises: why the sky is blue? So we know that now electromagnetic waves from the sun is coming to the environment, and in our environment we have a lot of nanoparticles. So the electromagnetics will, so our EM waves will interact with these nanoparticles, and these will scatter. So these particles are of the order of lesser than 1 nanometer in size, and so our omega naught is very very greater than omega because of smaller size. So it will not be a resonant phenomena, but it is a broadband response. So but that factor is get cancelled. So but now is directly proportional to omega to the power 4. Hence higher frequency means blue light has lower wavelength, that is 400 nanometer, and higher frequency. So in this case the more scattered light will be of blue, and we can see the sky we can see that the sky is blue. So next question is: why does at the time of sunset and sundown the sky is reddish? So sun is at the horizon, and the distance traveled by the distance traveled by light before it reach our eye is longer, and blue light is scattered in, since we saw that it is directly proportional to omega raised to power 4. So blue light is scattered in all direction, and only the remaining light that is coming, which is which scattered is minimum, is red, and that is actually reaching our eye. So that's why it looks reddish. Now why are clouds white? So clouds are white since particle size are very large, because what are the clouds? So there are water droplets essentially in clouds, and they scatter at the wavelength equally whenever the size of particle. So because they this large particles are scattering at the wavelength equally, that's why there is no particular color is visible, but we can see the white color of the clouds. So whenever the size of the particle is less smaller than the wavelength, there will be relay scattering. And when, so there is one other type of scattering, that is me scattering, which deals with the slightly larger particles. So now what will happen if light what will happen if light hits the metal nanoparticle? So plasmonics plasmonics is the science of interaction of light with metal. So we will see a different type of resonances. We will see a different types of plasmonic resonances, and to understand that what we see in like Maxwell's equation. So here, so there are various terminologies and types of plasmonic resonances. So plasmonic resonance refers to the coherent oscillation of free electrons in metals when stimulated by incident light, leading to enhanced electromagnetic fields at specific frequencies. So there are different types: surface and bulk plasmons. So surface plasmons are confined to the interface between a metal and a dielectric, while bulk plasmons exist within the volume of the metal, so each exhibiting unique dispersion relation. So, so what are the key terms between this? Transverse and longitudinal wave. Longitudinal waves. Transverse waves oscillate perpendicular to the direction of energy propagation, whereas longitudinal waves involves oscillations parallel to energy transfer, crucial for understanding resonances. So, and this is our Maxwell equation, that is k dot e minus k square e is equals to minus epsilon as a function of k omega square by c square e. So now we can see that this epsilon has this permittivity has a k dependence. So when we are dealing with, so epsilon permittivity has the dependence on size of particle, but this will happen if the particle size or thin film size is lesser than 1 nanometer. With large size epsilon will have dependency on frequency, so we can write directly like epsilon of omega. So for classification of various types of resonances, we consider whether the wave is transverse or longitudinal. So for the transverse wave, E is electric field is perpendicular to the direction of propagation, that is k dot E is equals to 0. And so k square we can write epsilon as a function of omega square by c square. So this is generalized dispersion relation for omega wave. And we saw in the previous lectures that for matters we get the dispersion relation 1 minus omega p square upon omega square into omega square by c square. So, so omega square is equals to omega p square plus c square k square. So this is the general dispersion relation when light interacts with the matter. So, so if we will draw the dispersion relation omega versus k, so for when light will when EM wave will interact in the free space. So when the EM wave, we have EM wave that is propagating in the free space, we have this relation, that is a straight line omega is equals to ck. But for matter, so using this relation, if we plot, then we will get that omega is equals to omega. So if we put omega is equals to 0, then we will not, we are getting that at k is equals to 0, omega is not equals to 0, which was in the case of free space. Now in the medium for metals, if I'm having k is equals to 0, then I have omega is equals to omega p. So my dispersion will not start from the k equals to omega equals to 0. Now it has some initial value that is equivalent to the plasma frequency omega p. So, what does this mean? This shows that these can exist only for frequencies greater than light. They cannot exist below omega is equals to ck. So, when this type of waves will interact, when this type of waves will interact with the matter, are known as the surface plasmon waves. So, so further this has the subcategory. So this has a subcategory when light will interact with the nanoparticle, then we say the localized surface plasmon waves. When the light will interact, so when we will have the interaction of light with interface of metal and dielectric, we call it the surface plasmon polariton as wave propagate. So these are the cases when we are having the transverse electromagnetic wave, that is k dot equals to 0. Now the another case happens when we will have the longitudinal wave. In that case, the wave vector is the parallel to the electric field. Extension. Screen recording. Then k dot e minus k square e. So we will go back to this in this equation. In this equation, this k dot e minus k square e will be equals to 0. This will be equals to 0, and we will have the epsilon omega square by c square equals to 0. So the trivial solution is no frequency because omega equals to 0. This is valid. Non-trivial solution is epsilon omega equals to 0. So this is for metals. So we know that for metals epsilon omega equals to 1 minus omega p square upon omega square. In this case, we can excite what are known as bulk plasmons. So these are known as bulk or volume plasmons. The interesting thing is we have longitudinal waves and they can't couple to the regular electromagnetic waves. Suppose if I'm incidenting a light, we cannot excite a bulk plasma since the incident electromagnetic wave is transverse and it cannot excite the bulk plasmas. But we can excite bulk plasmas with E-beam radiation. So next we will understand what is the quasi-static approximation. So quasi-static approximation simplifies the analysis of plasmonic systems by assuming spatial variation in fields are negligible over significant distances compared to wavelength. So induced there will be induced dipoles in metal nanoparticles. So the presence of an oscillating electric field induces dipole with nanoparticles, resulting in strong localized interaction that are central to plasmonic effect. And then electric field behavior. So now you can see that. Okay, so now I can write. My screen is connected. So what is the quasi-static? So what is the quasi-static interaction? So our E is interacting in matter. So here in this case, what will assume? So suppose this is our electromagnetic wave, and this is our assumption that we are considering the electric field is constant over the size of nanoparticle. So what does this mean? So we can see that this is a wavelength. So if we the wave is propagating like this, and we have such nanoparticle. So in this case, the electric field is always constant. So this is valid when condition, what is the condition for this approximation? That is D is greater than 7. So this is my quasi-static QS approximation. So now when the light sorry, under the presence of electric field, when light interacts with the metal nanoparticle, there will be a separation of charge, and because of this separation of charge, there will be an induced dipole, and that will be equivalent to, since the we know that in the atoms, the electric field inside the nanoparticle is zero. Therefore, E incident, E induced will be equivalent to that is so we define the cross section sigma p polarization equals to 3 epsilon 1 minus epsilon 2 epsilon 1 plus epsilon 2 E naught cos of theta. This is very important and we have several problems regarding this where E1 is the permittivity of metal and epsilon 2 permittivity and here E naught cos of theta. This represents density of charge. So this is electric electric field inside and it has so we one interesting thing we are showing charges like this but not like this. Why this? So why is this? Is this? So we have like but not this. So because so tangential so the tangential is continuous. So electric field inside is zero and has continuous tangential. So we can have the flux the jump. So now here cos theta directly tells us that the charge is separated along the direction because of cos theta. So charge is separated along the direction that is and we can along the direction. So there's one more. So density. So cos 90 also in the polar direction lesser density of charges reduce in polar. So, what does this mean? So, we can say that epsilon. So, now we have seen the induced dipole in the matter nanoparticles. So, the presence of an oscillating electric induces dipole within nanoparticles resulting in strong localized interactions that result from magnetic effects. And how the what will be the electric field behavior in nanoparticles? So analyzing the behavior of electric fields around nanoparticles reveals how localized surface plasmon resonances can be fine-tuned for specific applications. So next is so introduction to localized surface plasmons. So we saw that. So we have a different category that we are having the interaction of light with another dielectric interface, then say the surface plasmon with light interact with nanoparticle, and then we see the localized surface. So LSPR. These are LSPR refers to LSPR. So LSPR refers to collective oscillations of conduction electrons in metallic nanoparticles, which are specially confined and occur at the nanoparticle surface when exposed to EM radiation. So, what is the importance in nanotechnology materials? So, these plasmas play a crucial role in enhancing light matter interactions, and we have various applications of this in sensing, imaging, and photonic devices. So, their unique characteristics make them vital for advancing nanotechnology and materials science. So, next we will overview of excitation methods. So, excitation of complex surface plasmas can occur through various methods, including optical excitation from lasers and other light sources. So, we will understand these. So, if we will understand these methods, these are the key points to harness their potential in technical application. So, next thing is methods of excitation with field microscopy comparison with other techniques. So, excitation methods for localized surface problems include strategies such as laser illumination, E-beams, so that we cannot excite the bulk plasma if I am shining the EM directly, but with the electron beam irradiation, I can excite the bulk plasma. So this is the methods of excitation, and each method exposes the nanoparticle to varying intensity, leading to variety of responses. So next, how can we see the nanoparticles under the microscope? So for seeing the nanoparticles, we have the dark field, which is a particularly effective method for exciting the localized surface plasmons because it allows for communication of particles against a dark background, enhancing that enhances the scattering signals from the plasmons. So when compared to other techniques, like so we have both modes in our microscope, that is bright field microscopy and dark field microscopy, fluorescence. So as compared to other techniques, dark field microscopy offers enhanced contrast intelligence for monitoring the plasmonic effects impressively. sorry, revealing size and shape dependent properties. So in this figure, you can see that we have our sample. These are the particles, and on the top of the particles, there are detectors. Light is coming, and it is like scattered, and it is going to in the bright. See that we are not able to see clearly the color, or we can observe the nanoparticles, but in the dark field where we are observing only the scattering through the nanoparticles, we can see the different colors of the nanoparticles. You can see that red, yellow, green, blue. So first of all, these are clearly visible. The color, these colors are different because of different sizes of the nanoparticle. So because of figure C, in this figure, you can see that there is spherical nanoparticle and the nanoparticle. So, and these are differing in sizes, dependency on sizes. They will have different colors as well as the different resonances. So you can see that for the spherical one, it has a resonance around 450 nanometer. And as the nanoparticle size increases, the resonance is getting shifted towards the lower level. So next we will study the characteristics of nanoparticles, how the resonance is getting shifted depending on the shape, size, shape, and location. So the optical properties of particles, particularly their surface plasmon resonance, are highly dependent on size and shape, leading to divergent responses within the spectrum. And the resonant wavelength, each particle has a distinct resonant wavelength, characterized by the wavelength of light that indicates its surface plasmon. So that will fundamentally influence the particles applications in photonics and sensing. So as the size of matter and particles changes, diameter color can vary significantly due to shifts in the resonant frequency, which can be precisely tuned for specific applications by controlling the nanoparticle dimension. So we saw that we consider the theory for the nanoparticles. We consider the scattering cross section. So Ning theory provides an analytical framework to describe the scattering behaviors by spherical particles, accounting for the effect of size, shape, reflective index, and wavelength, so that we can understand the quantum behavior. And the scattering cross section is a key metric that quantifies the probability of scattering events occurring. So it can be calculated using mean theory equation that is equal to the nanoparticle size and the properties of the nanoparticle. So as the dimension of the wavelength of density, scattering efficiency dramatically increases. So that will influence both absorption and scattering behaviors, essential for applications utilized on the plasma. So now what? So if you have if you have like the current represent the theoretical considerations for optimizing light system. So if you have the small size particle, you have that, and as the size increases, then there will increment in so that it, particle from dipole. So we will have expressions of distributed temperatures from the particle temperature significant intensity variables determined by particle geometry and excitation wavelength leading to localization of spectral temperature. So with particle size, so it will transform to quadruple hexapole. So as the size of the particle changes, the nature of the electrical distribution evolves factors such as shape and modulate this distribution. So that will eventually affect the plasmonic characteristics. So in this figure, you can see that for when the particle size increases from the diameter of 50 nanometer to 150 nanometer, there is an involvement of the electrodes also. Earlier it was single, but with increasing particle size, the resonance also, the FW is also increasing, and the peak is getting broad. And after 150 nanometer, there is a sharp peak that shows there are participation of higher orders. So we know that the restoring force is given by k by m. As the wave vector increase, omega naught will increase, and the lambda naught will increase. So by increasing the size of the particle, it will the resonance peaks will shift towards the long wave. So this is what I was saying, that d is equals to 50 nanometer, and d equals to 50 nanometer. Lambda is equal to 55 nanometer. It is again diagonal, with lambda is equal to 367 nanometer. That's a so we saw that this is the size of the resonance. And so electrons scatter at surfaces. It is given by gamma r is equals to gamma naught plus avx upon r, where vf is the Fermi density, and a is a scattering mechanism correlation. So this will depend on size dependent. This a will change into size. So this is regard to the dark field. And then this resonance wavelength depends on two main factors, that one is optical constant of the surrounding the electric. Second is shape and size of particles. So we have nanodots, nanoshells, nanocages. So all these have the different resonant wave. So how can we understand this plasmon hybridization? If we have a sphere and in the presence of electric field, there is a charge separation, and it is given by omega s is equals to omega b by root 3. And this is we have omega c equals to root 2 by this induced polarization. When these two will interact, when these will, so they show to hybridize bonds. One is bonding or symmetric mode, and the other one is anti-symmetric or anti-bond. So The symmetric will have lesser energy, and you can see that here there is a generation of positive, negative, negative, positive. So there is a large net dipole moment. If there is a large net dipole moment, then there will be more radiation, and it will. So if the radiation will be radiated losses very large, then we will have the larger accumulation. So it is larger width with the radiated losses. And in this case, anti-bonding case, we can see that the positive, negative, and negative positive. So there will be these will not couple efficiently to the free space, and that dipole will get reduced so that we will get the low losses. So we will get the smaller. We plot omega versus t. So symmetric will have lower frequency and different will have higher frequency. So in real world application, we are using different photovoltaics, ultra-sensitive diagnostic. So we are functioning with some sensitive material which we want to detect. Similarly, plasma color filter. So then we will about surface plasma polarity. So in transverse wave, we have two cases: LSP and localized surface plasma resonance and surface plasma. So in the surface, like, earlier we did deal with LSPR, in which the waves interact with the nanoparticle. Now, in for the SPP, we will talk about the light interaction with the matter-electric interface, and we will have SPPs, and which is known as the collective charge oscillation and conductor-insulator interface. So, SPP wavelength is denoted by SPP, which is smaller than the free space wavelength. So, in real applications, we need generally bring waves so that we can guide our SPPs. So, if I am fabricating some waveguide and if I am exciting SPPs, then these SPPs will propagate through waveguides or nanoscale optical fibers. So this is what light and electric metal interface. Here we have the metal dielectric interface and the here the metal permitting will be lesser than zero, and epsilon D is epsilon dielectric interface which is greater than zero. So from this we can see that kx. So this is a dispersion relation. So for the kd, for the wave vector in dielectric, in the y-axis it will be zero, and kx k0 minus kz. Similarly for k metal, so if you will write the dispersion relation kx square kg square, see just see these coordinate system which is given by epsilon and square. So if this k to z is imaginary, so light will not penetrate into the metal. Light will be reflected. So now the reflection from silver. So you can see in this plot that wavelength versus reflectance. So there are three thicknesses of silver given 10 nanometer, 1 nanometer, 1000 nanometer. So if you will see in this, for the thinner film, you can see that the is increasing with the wavelength, but the reflectance is not going to 1. But as the thickness increases, you can see that there is a sharp change, and it is at the Plasmon frequency, omega p or lambda p, the reflection goes to 1. Means the light is transmitting. So we can say that, we can say this graph that for the highest reflectance will be higher as to the thin film thickness. So for the and the light is getting, so reflectance is less than 1, only the light is getting transmitted. So we can say that for the epsilon m, you can see this plot. Epsilon m is lesser than 0, for omega is lesser than omega p. and for omega is greater than omega p, the light will be transmitted. So response, so surface plasma polariton response depends on whether we have the transverse magnetic waves or transverse electric waves. So if I'm saying transverse magnetic wave, that is we will have only the Y component and the X and Z component will be zero. For the case of transverse electric waves, electric field, transverse electric field will have the Y component of electric field and X and Z direction will be zero. So if I'm having H1y equals to H1 at a k equals exponential minus at a k. So what we can say is plane wave is propagated in x direction and evanescent wave in z direction. We will solve question depending upon these using these equation and the SPP dispersion. So let's move to the so let's move to the question related to the surface plasma polarity dispersion. So we are considering the waves. The wave is consider the wave equation given below and choose the wave properties for the photonic. So gi- we are add the kx exponential minus delta kz and it is given that it is written. So from this we got that this is equal to we have only hy component and this component represents some traveling wave based on propagating propagating plus x direction with the wave vector kx and this term kz is a real exponential decay. Since kz is greater than 0, so we can say that amplitude is decay. So what are the options? Wave is propagating in z direction. No, wave is propagating in z direction. Wave is propagating in x direction. Yes, and balance in direction. So this option is correct. Next is wave is propagating in x whether it in y direction. So this is true, but this is not. So the decay is z direction. So second question is when the light is on matter dielectric such that epsilon 1 and epsilon 2 is permittivity of dielectric and matter respectively. It undergoes a SPP, the wave equation. This, which of the following is true? permittivities. So it is saying that it's a surface plasma. So we know that a surface plasma polarity SPP exists at metal dielectric. So and it will occur when real part of epsilon 1, real part of epsilon 2 is lesser than 0. So we have dielectric which has epsilon is greater than 0 and metal epsilon 2 is, so it means epsilon 1 and have signs. Next question. Consider a dielectric interface whose relative permittivities are positive and negative respectively. So when light is incident on it as shown figure, which of the following is oh really why is that? So what are the options? Light is absorbed within the skin depth, light cannot propagate in matter intensity, light is transmitted due to magical effect, or light is transmitted due to no defective. So in dielectric epsilon d omega is greater. What does this mean? It means that the wave vectors, if this is real, we have the propagating light. But in case in metal, so the light is propagated from the dielectric to the metal in metal, epsilon m as a function of metal, 0. So what is our dispersion relation? Km is equals to omega by epsilon m. So we know that epsilon is a function of this. So our wave vector. So Km is imaginary. So if it will be imaginary, what does this mean? So if there is no probability, there is an exponential rate. So if we are considering our option in that 0, so light is reflect. The right answer is propagating matter, it is reflected. The next question is reflected from two silver films of different thicknesses are shown below. Which of the following is correct regarding the thickness? So we just saw. So for the T1, high reflectance. and T2, lower reflect. We just saw that thicker blocks light more effective. And so in the increasing with the but not reaching to the one. But for red, it is reaching to the one. Hence, T1 is greater than. So the option B is correct. Next question is consider light P1 and made of same metal which are resonant. So the normalized scattered intensity of these light as shown in. So now it is that 2 nanoparticles, same metal. So same metal means but different resonance. Resonances. This can be possible. Different size. So LSP LSP ratio as particle size increases. We just saw that the frequency is lower in the spectral case, the wavelength will increase toward the longer. So blue peak is at the top, pink peak is the smaller wavelength. So blue peak has the higher geometry. So the answer P2 has higher. Then matter and the number of particles per unit for the different metals, copper, silver, gold. So the and to get the electrodensity at room temperature for different metals is given below. Assume the effective mass and star equals to E equals to 9.1 into 10 to the power minus 30. And permittivity is permittivity constant is 8.85 minus F by M. So the question is the plasma wavelength and plasma frequency, plasma energy, calcium. So we want to find out the plasma wavelength and star equal epsilon naught, and these things we want to calculate omega p. So for that, so we want to find out the plasma wave. Since lambda p is equals to c by fp, for fp we want omega p is equals to omega p is equals to n square. So if we will the value is 4.61 into 10 per meter cube. So after substituting 1 into 10 raised to power 60 radians per second. If we have the omega p, we can lambda p. So this will equivalent to 1 raised to power, or we can say 56. The next question, omega p. We want to find out the plasma energy is h cross theta, which will give you seven. So the 150 and 8. So the option C is correct. Next question, the plasma wavelength. So the plasma wavelength is lesser than greater than equal to 10 times or 100 times the plasma wavelength of light. So in the table, it is given that NCU is 7 into 10 raised to power 20 per meter cube, and the gold 5.90 into 10 raised to power 20. So we can find that is lambda p 2 pi c omega p n a square and star epsilon. We can say that omega p is proportional to 1. Okay, so we can say lambda p is 1 by n. So lambda p lambda p is equals to n into n c. So it is 5.0. So we can say that lambda is less. So answer first is correct, that we is less than plasma. Next question is when the light frequency omega is incident on the interface of relative permittivity epsilon 1 epsilon 2 and epsilon 2 is equals to minus of epsilon 2 equals to 1. What is the frequency at which SPP wave vector becomes maximum? So we know that what is the dispersion for the metal dielectric is surface plasma polarity dispersion. For metal dielectric KSPP is equals to K naught is omega. So epsilon 1 is equal to 1 and epsilon 2 is epsilon D dielectric. Epsilon 2 is epsilon of matter as a function. So we can write KSPP is K epsilon m 1 plus epsilon. So according to Drew, when we are considering epsilon m omega is to omega p square. So this SPP wave will diverge when 1 plus epsilon of m goes to 0. That is epsilon equals to minus 1. So we can substitute the value as omega p square is equals to minus omega p square and omega is equals to root 2. So this is the frequency at which the surface of the Polariton wave vector becomes maximum. So next question. Consider two spaced vector particles. Which of the following statement is correct? The first statement is that the frequency of antibonding mode is higher than the antibonding mode. Second, the antibonding mode exhibits lower resonance compared to the bonding mode. The bonding mode couples strongly to free space radiation when compared to the antibonding mode or one of the option. So the first option. So we saw that we will have the closest two particles. The two particles diverge hybridize into lower energy bonding, which is in phase mode, lower energy bonding, which is in phase, and then high energy anti-bonding mode, which is out of phase. So the anti-bonding resonance will be at higher frequency. So the first is correct. The second is anti-bonding mode except lower resonance. So we saw that if the bonding mode is a dipole, okay, so bonding mode is large, the bonding mode is, and therefore it will radiate more, and it will be able to couple more easily with the free space, so it will produce shorter length. So in that case, the anti-modeling will exhibit the longer resonance. So the second option is also correct. And if the larger matter bonding would couple strongly to free space radiation as compared to the anti-bonding, since it is a dark mode and reduced dipole, the net dipole is gets reduced, so it is that's radiated and it shows an active line width. So all of the options are correct. Next question is gradual configuration to excite propagating pulses applied in the electric interface through a glass prism. Which of the following schematic depicts the excitation condition for propagating surface plasma of wave? So you can see the four figures A, B, C, D. In figure A, the, the plasmon wave vector is propagating on the inner area. So this is so we are talking about the surface plasmon polariton. So it should be the outer surface. So in the figure B, we can see that our polariton is propagating on the surface, and in the figure D, it is propagating outside the surface. It is the A surface. So we have to choose and see. So we know that the SPP propagates on the outer interface, and the field will decay evanescently into the dielectric and into the metal. So coupling will occur by the evanescent wave produced by the DIR in the prism that reverse within the. So the panel, it is not on this direction. In this reason, the SPP will not propagate along the interface. So that's why optical shades the vector and option B is the correct option because it is showing that coupling is occurring by the evanescent wave and only on the outer surface. So option B is correct. So next question is a metallic sphere of radius 15. So if it is radius is equals to 15 millimeters, means what does it imply? Quasi-static approximation is valid. So here, what is the metallic sphere of radius 15 millimeters? Epsilon d is equal to 1.5, and permittivity we have to find out the permittivity of the metal for which the polarizability exhibits the maximum amplitude. So we wrote one equation. Uh, we wrote one equation. Epsilon m. So in this case, we are using this approximation. That's 0. Epsilon m plus is equals to 0, and we have that m is equals to minus 2 of epsilon d. Epsilon d is equals to 1 point condition for maximum. So epsilon m is so epsilon m is so minus 3 to correct. Next question is matrix. The matrix nanometer justifies the quasi-static sizes less than the plasma frequency electric environment of permittivity. The condition for excitation of localized surface plasma when light of certain frequency makes. So we have to find out the frequency at which the SPF will be excited. So we know that S is equals to, this is polarity, 4 pi into epsilon m epsilon d epsilon omega plus 2 epsilon and so LSP occurs when this condition is is equals to 0. So real part of epsilon m is equals to minus 2 epsilon. Okay, so we will remind this. Next, epsilon m of omega is equals to minus omega p square by omega square. So minus 2 into 4 is equals to this condition. So omega p square. So omega is equals to omega p by 3. This is the frequency in terms of gamma frequency where the LSP are roots. So the correct answer is the last option omega is equals to omega p by 3. So this was all about the sine wave. Next we have few questions from the book. So the question is saying show that the resonance of the collapsibility of matter nanoparticles that always equation 7.7. So this is equation 7.7 occurs at an angular frequency given by omega p upon 1 plus 2 n square under root in a medium with a respective index of frequency for the gas by the dielectric. So just now we have solved two questions similar to that, and we have told how can we get this formula, that is thermal formula when the dielectric is there. We have to prove what we have to prove here. So to prove omega is equals to mt by 1 plus 2 n. So using this equation, alpha is equals to 4 by AQ. So resonance, when will the LSB be when this condition will be satisfied. So from this condition we get to so if we will, so since epsilon d is equals to n square and epsilon of omega is equals to 1 omega p square by omega square. We will substitute the value minus 2n. So now 1 plus into omega square to omega p square. So we want to find out the frequency. So this is going to denote to get that plus 2n square. So if the is equal to 1, is equals to p root 3. And the next question is the surface plasma known with the frequency corresponding to vacuum wavelength of 600 nanometer is excited at the interface between silver and air. The relative permittivity of silver at this frequency is approximately by m is equals to so we have imaginary component also. We have both the parts here. So we have the complex relative permittivity. So first question we are asking the calculator KZT and KZN. So in this right figure you can see that this is for the metal and this is for the electric metal. So we have to calculate the decay constant and then reduce the field decay length in the direction of the metal. The first part, for the first part, we are ignoring the imaginary part of epsilon m and we are putting, so since it is silver air, for air the epsilon m will be 1 and since m equals to 1. So we have these two formulas in which for the electric wave vector it is this is k naught omega by c minus epsilon d square upon epsilon m plus epsilon d to power. So omega is 2 pi nu. So nu is equals to c by lambda. So c we are given lambda is equals to 600 nanometer. C will be cancelled. 2 pi by lambda we will substitute the value of epsilon d and epsilon n. So we will get the 2.5 to 10 to the power 6 meter. Similarly, we can calculate for the metal also. Since we have equals to minus 8, we will substitute the value of minus 8 and put this. To find out the decay depth, we will do 1 kd. So if we will do 1 kd, we will get the 3. Similarly, for it is, so we can see that at the concentration, the skin depth of metal is of the order of 29, the silver at 600 nanometer. And for the electric, it is large. The decay is not very sharp, and the light can penetrate to longer distance. If we have a director, so it is of 394. The second part, in the second part is asking that the propagation length in the direction parallel to the surface is defined as the distance over which the intensity drops by a factor of by E. Calculate the imaginary part of kx and hence reduce the propagation length for silver at 600. So the propagation length direction is determined. So we are asked propagation length. If we are considering the length, then we have to consider the imaginary part of kx. So we are including the given epsilon m is equal to minus 18 plus iota. So using this formula kx is equal to omega by c epsilon m epsilon t. So kx is equal to 2 pi by this. Just we have considered imaginary part. So minus 18 plus iota into 1 minus 18 plus iota plus 1. It will give us it is minus 17 plus iota. Solving this, we will get this. So, if we want to write the wave equation, how the wave is propagating, we will have to consider the k prime and k double prime. So, E naught exponential item kxx, where kx is equals to k prime x plus k double prime x. So, intensity proportionally epsilon epsilon star and our 2k double prime x. So, the propagation distance will be equivalent to 1 by 2k prime. So, k prime goes 1.8. So, 1 by 2 into 1.8 into 10 raised to power 4, which will be equivalent to 28 micrometer. So, this is the propagation. So, thank you so much. This was all about. See you on the next.